Welcome viewers. In this video we'll see the construction and operation of single phase induction motor. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, construction and operation of single phase induction motor. Normally the single phase induction motor is a small size motor used in domestical purpose with a fractional kilowatt rating. Three-phase induction motors are used for industrial purpose with more power rating. The single-phase motors are less power rating, small size, mostly used for the domestic purpose. So it is based on the electromagnetic induction. The working principle of this single-phase induction motor is the principle of electromagnetic induction to create the rotating magnetic field. Now we'll see the diagram of a single phase induction motor. Normally in single phase induction motor, if we have only one phase, then the net flux will be zero. For example, so this is the alternating voltage we are applying. So the alternating AC voltage is applied, so the flux also produced in alternating nature. If only one winding available means this is the positive flux, this will be negative flux, positive off cycle, negative off cycle. So the flux produced in the positive off cycle is positive, during negative off cycle is negative, so both got cancelled. The net flux will be zero. The flux, this is the flux will be zero if we use the only one winding. Because of alternating nature, positive and negative alternatively changes, so the net flux is zero. So normally in single phase motor we are using two windings. See this, running winding and starting winding. This running winding is connected directly, starting winding is connected through the capacitor. What is the nature of the capacitor? It will lead the current. So the current is lead in the starting winding and current in the running winding is normal. So what will happen? We'll see the diagram. So this is the flux produced in the running winding. But in case of starting winding, the current will leads. So there is a phase difference. There is a phase difference between starting winding and running winding because of capacitor. Now the flux is not zero. Always some amount of flux will be available. So that flux is used for rotating the motor. Right? So in single phase motor, induction motor, if you use only one winding, the net flux is zero. So we are converting into two windings called starting winding and running winding. This starting winding is connected with the capacitor, so the current leads. Running winding is connected normally. So there is a lag, there is a phase difference occurs between the current flowing through the starting winding and running winding. So there is, due to the phase difference, always some amount of flux is available in the motor. So that flux is used for rotating the induction motor. Now we'll see the full diagram. So we know that the induction motor, normally in motor we have rotor and stator. Rotor is a rotor, squirrel cage rotor. Rotor is the rotating part, and stator is nothing but a stationary part contain the windings. Right. First we will see the rotor. This rotor is a squirrel gauge rotor. Like three-phase induction motor is a squirrel gauge rotor. Squirrel gauge rotor means it contains the slots in a skewed manner, not a parallel manner. It is available in a skewed manner. Skewed manner means so that the losses will be reduced. In these slots, the copper, aluminum or brass the bars are available. Permanently bars are placed, not a coil. It contains the aluminum bar or brass or copper bars are placed. So that will be connected in a closed circuit. It will act as a closed circuit. So the rotor is a squirrel gauge rotor, contain the skewed slots. In that skewed slot, the aluminum bar or copper or bronze bars are permanently placed, not a coil. Permanently bars are placed. All bars are connected together, so it will act as a closed circuit. Right. So this is the nature of the rotor. In case of stator, we have stator winding, stator slots are available, in that the coils are placed. Here the two coils available, running winding and starting winding. This running winding L1, starting winding L2. So the starting winding is connected through the capacitor and centrifugal switch. So we already discussed, due to these two winding, this L1 is connected directly to the supply, L2 is connected through the capacitor. So there is a lag between starting and running winding, due to that some amount of flux always produced. So that flux will develop in the motor. If only one winding means the net flux will be 0. So due to the flux, this rotor, the EMF is induced in the rotor. Whenever there is a rate of change of flux, EMF is induced in the rotor. This rotor having copper or aluminum bar that are closed circuit. So due to the closed circuit, current is flowing through the squirrel cage rotor. Current is flowing through the rotor. Now this will act as a current carrying conductor. Whenever a current carrying conductor placed in the magnetic field, it experiences a force. So due to that, it will start rotates, right? When it is rotates, due to the force, because of centrifugal switch is connected, the switch got open and starting winding is disconnected. So the starting winding used only for starting purpose. That's why it is named as starting winding. After, once the motor start rotating, due to the centrifugal switch action, it is disconnected. Starting winding is disconnected. Now the motor will start rotate in a normal speed, the rated speed. So here we have rotor and stator. Rotor is squirrel cage rotor. Copper bars are available from the closed circuit. Stator, we have starting and running winding. Running winding is connected directly. Starting winding connected through capacitor. So there is a lag available. There is a phase difference available between two windings. So the flux produced also having the phase difference. So the net flux always available. That flux will create the EMF in the rotor. Due to the EMF, current is flowing through the coil, flowing through the bar. So it will act as a current carrying conductor. This current carrying conductor placed in the magnetic field will experience a force. Force means it will start rotate. Once it is start rotating, due to the centrifugal action of switch, this switch is disconnected. Switch is open, so the starting winding is disconnected. So starting winding used only for starting purpose. Thereafter it is disconnected. So this is the operation and construction of the single phase induction motor. Now we'll see the description. These details are available. What we discussed, the details are available. We'll see this one by one. So the construction. So like the other electrical motor, asynchronous motor. So the induction motor normally called as asynchronous motor. Synchronous motor means always rotated in rated speed, but this is not rotated in rated speed. When the load increases, speed will decrease. The two main parts are rotor and stator. What is stator? It is name indicates. Stator is a stationary part of the induction motor. A single phase AC supply is given to the stator of the single phase induction motor. So stator is nothing but a stationary part. In that AC supply is given. Now we'll see the rotor. The rotor is a rotating part of induction motor. It connects the mechanical load through the shaft. The rotor in the single phase induction motor is a squirrel cage type of rotor. So the rotor, stator is a stationary part, rotor is a rotating part. The mechanical load is connected through the rotor through the shaft. It is a squirrel cage type. Now we'll see the stator of the induction motor in detail. Now we'll see the description. I will see in detail what is the stator, what is the nature of stator. The stator of single phase induction motor has laminated stampings. The stampings are laminated in order to reduce the eddy current loss on its periphery. So it contains the laminated stamping to reduce the eddy current. The slots are provided with stamping to carry the stator or main winding. The stamping means there is a place in which the coils are placed. some space will be there, in that the coils will be placed. I will see the further detail. These stampings are made up of silicon steel to reduce the hysteresis losses. Right? So the laminated stamping already available to reduce eddy current loss. Now it is made up of silicon steel to reduce the hysteresis losses. When we apply a single phase AC voltage to the stator winding, the magnetic field gets produced and the motor rotates at the speed slightly less than the synchronous speed. So when the AC supply is given, what will happen? Magnetic field will be generated, what we discussed earlier. The speed of the motor is nothing but ns 120 f by p, synchronous speed, but it is slightly less than the synchronous speed. Ns equal to 120 f by p. What is that? This f is nothing but supply voltage frequency. P is the number of poles of the rotor. Now we will see the further detail. The construction of stator of the single phase induction motor is similar to the three phase induction motor, except there are two dissimilarities in the winding part of the single phase induction motor. So almost it is very similar to three phase, only two major differences are available. Now we'll see what are the differences. First is, single phase induction motor are mostly provided with concentric coils. Yes, concentric coils are available. We can easily adjust the number of turns per coil with the help of concentric coils. The of distribution also sinusoidal. It's not a distributed coil, it's a concentric coils are available. So we can easily adjust the number of turns. That is the first difference between the single phase and three phase. In all types except for shaded pole motor, an asynchronous motor include two stator winding, the main winding and auxiliary winding. These windings are positioned at right angle to each other in what is known as space quadrature. So we already this is starting coil and running coil. So here it is named as main winding and auxiliary winding. Then only there is a flux will be produced. Only one winding available means the flux is 0. So that we have main and auxiliary winding. So in three phase induction motor, automatically three phases are available. So the flux will be produced automatically. But here we have two windings. We are using two winding, main and auxiliary. That is the one difference. Another difference is concentric coils are available. Now we'll see the rotor or the details about the rotor of a single phase induction motor. The construction of rotor of the single phase induction motor is similar to screw gauge three phase induction motor. Screw gauge means the copper bars are available. The rotor is cylindrical and has slots over its periphery. It's a cylindrical type. Now we'll see the further detail. The slots are not made parallel to each other, but it is little bit skewed. I already told. It is not a parallel, skewed. The skewing prevent magnetic locking of stator and rotor teeth and makes the working of induction motor smooth and less noisy. Normally it is parallel, but here not a parallel, skewed to avoid the magnetic locking between stator and rotor so that it will rotate smoothly and with less noise. The screw gauge rotor consists of aluminium, brass or copper bar. I already told, not contain any coil, contain the bar. Aluminium, brass or copper bars are available. These aluminium or copper bars are called rotor conductor and placed in the slot on the periphery of the rotor. In the periphery, these bars are placed. The copper or aluminium rings permanently short the rotor conductor called the end rings. So it is closed circuit. I already told it is closed circuit. So permanently it is short circuited to form the closed path. To provide mechanical strength, these rotor conductors are braced to the end rings and hence form a complete closed circuit resembling a gauge. Hence got its name as screw gauge induction motor. So it is completely form a closed circuit. In order to give the mechanical strength and form the closed circuit is available, so that it is called a squirrel cage induction motor. As end rings permanently short the bar, the rotor electrical resistance is very small and it is not possible to add external resistance and bars get permanently shorted. In case of three-phase induction motor, we can externally connect the resistance because of the construction, but here it is permanently connected, so we are not able to connect any external resistor. That is the point given here. So that external resistance used for speed control, here it is not possible to add any external resistance. Now we'll see the further detail. The absence of slip rings and brushes make the construction of single phase induction motor more very simple and robust. Right? There is no slip ring and brushes are available. If slip ring and brushes are available, mean there is a noise will be there, then there is a maintenance we need to replace in a frequent manner, but these are all not available in that, so that it is will be very simple. Construction is simple and robust. Though now this is the construction, stator and rotor. Now we'll see the working principle of induction motor. What we discussed, the description is available. According to Faraday's law of electromagnetic induction, EMF get induced in the rotor. So when the supply is given, flux is produced in starting and running winding because of phase difference. That flux will link with the rotor. Due to that electromagnetic induction action, EMF is generated in the rotor. As the rotor circuit is closed one, so current start flowing through the rotor. This is called a rotor current. I already told the copper or brass or aluminum bars are available. They are connected with the end rings. So it will act as a closed circuit. Due to that current is flowing. That is called a rotor current. Now the rotor current is flowing. The rotor current produces its flux called a rotor flux. The rotor current also flux one more flux. Since this flux is produced due to the induction principle, so the motor working on the principle, it is named as induction motor. So this is induction between stator and rotor, EMF is produced. Due to the EMF, the rotor current is flowing. Due to the rotor current, another one more rotor flux is produced, so that is called a induction based on the induction principle. Now there are two fluxes. One is main flux, another is rotor flux. These two fluxes produce desired torque which is required by the motor to rotate. So I already told, when a current carrying conductor placed in a magnetic field, it rotates. So it will be start rotating with a desired torque. So this is the working and construction and working principle of a single phase induction motor. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the double field revolving theory available in the single phase induction motor. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, double field revolving theory in single phase induction motor. As the name single phase induction motor, we are not using single phase winding. While using single phase winding, the net flux produced is zero. So this theory explains how the net flux is zero in a single phase. Because in single phase, during positive off cycle, the flux is produced. During negative off cycle, the flux is produced is a negative. So both are got cancelled. The net flux is zero. Flux produced by positive off cycle is cancelled by flux produced by negative off cycle. So this theory explains how it is zero. For that reason, we are using two phases in a single phase induction motor, starting winding and running winding. In order to make the net flux, in order to create the net flux, we are using two windings, starting and running winding. After motor starts running, the starting winding is disconnected, only the running winding will be available. The principle of operation of induction motor, the separate video is available. So this double field revolving theory explain while using only one winding how the net flux is zero. Step by step it will explain. This theory makes use of the idea that an alternating uniaxial quantity can be represented by two oppositely rotating vectors of half magnitude. So the alternating uniaxial quantity we are going to deal, that is divided into two oppositely rotating vectors. Right, the net flux is divided into two half, both are oppositely rotating. Okay. Then we'll go to the next detail. Accordingly, an alternating sinusoidal flux can be represented by two revolving flux. Right? So it is divided into two, that is represented by the two revolving flux, each equal to the half value of the alternating flux and each rotating synchronously in opposite direction. Right? So we have two fluxes of equal magnitude, what is rotating in opposite direction. We know that synchronous speed n is equal to 120 f by p. F is frequency, p is the number of volts. Now we refer the diagram A. So this is the net flux, maximum value of flux pi m, that is now divided into two equal parts, pi m by 2 A, another pi m by 2 B. Right? The total flux is divided into two halves with A and B all rotating in opposite direction. A rotates this direction, B rotate that direction. Both are in opposite direction. As shown in diagram, let the alternating flux have a maximum value of pi m. Its component flux is A and B will each of equal to pi m by 2, revolving in anti-clockwise direction and clockwise direction respectively. Right? So the maximum flux is pi m, that is divided into two equal parts, pi m by 2 A and B. Right? This B rotates in clockwise direction, A rotates in anti-clockwise direction. So step by step we see how the net flux is 0 while rotating in this direction. So this diagram A now we refer. Now we'll go to the next diagram B. Refer this diagram B. So after some time, when the A and B would have rotating through the angle plus theta and minus theta as shown in the diagram. We know that A is rotating in anti-clockwise direction, B is rotating in clockwise direction. After some time, it is in this position with an angle theta plus theta and minus theta. So this vector sum of these two is the resultant, pi m cos phi. By using the parallelogram theorem, we can find the resultant vector, that is the vector sum of A and B. Right? So initially at this position A and B, after some time it is rotating clockwise direction as well as anti-clockwise direction. At the time we are got this diagram B. It is rotating, we are assuming that rotating at an angle of theta plus theta and minus theta. This is the resultant flux. Now we'll see the what is the resultant flux, the expression. We'll see the expression. So the resultant flux by using parallelogram theorem, it is 2 into pi m by 2 cos 2 theta by 2. So 2 got cancelled, here also 2 got cancelled, it is pi m cos phi. So the resultant flux will be pi m cos theta. Now it is in theta. Now we'll refer the diagram C. So after some time, initially A available here rotating in anti-clockwise direction at an angle theta, we referred B. Now it is available in this position at y-axis. The A is available at y-axis. Similarly, B rotating in clockwise direction, initially at this position in diagram B at an angle of minus theta, now available in this vertical manner, y. Right? So A available at the top, B available at the bottom. After a quadrature cycle means it is approximately, it is a 90 degree. Flux A and B will be oppositely directed as shown in the diagram C. So the resultant flux would be 0. Right? So A positive, B negative means both are got cancelled, net flux will be 0. Right? So initially at this position in diagram B at an angle theta, in diagram C it is oppositely, it is both are in opposite direction. A available at the top, B available at the bottom. So the net flux is 0. Now we'll see another two diagram. Just keep on rotating. This flux is keep on rotating. So after some time, the A start rotate from the top of this position. It will go to up to at this position A. Similarly, B initially B available at the bottom, still keep on rotating in clockwise direction and available at this position. That is exactly opposite to that of the diagram A. In diagram A available this side. Now diagram in the D available that side. Now it is minus pi m. So this side, while referring diagram A, it is plus pi m. While after rotating to diagram D, it is minus pi m. Still these two are rotating continuously. So the now A available here, B available here. B will still rotating in clockwise direction, A rotating in anti-clockwise direction. So A will come down and B will go to upward, right? Now A available bottom, B available at the top. So here also both are in opposite direction. The net flux is 0. Now we'll refer this diagram. This diagram C, A available at the top, B available at the bottom. In diagram E, A available bottom, B available at the top. So still it is 0. So the diagram A, the flux is pi m. We'll go to diagram D, plus is minus pi m. So got cancelled. In diagram C, A available top, B available bottom, net flux 0. In diagram E, B available top, A available bottom, still both are opposite, the net flux is 0. So step by step we are analyzing. In each cases, one flux produced in one position is cancelled by the other position. So that is our aim. How the resultant flux is 0 in a single phase winding. Now refer the another diagram, flux diagram. This is the angle theta. So initially 0, 90 degree, 180, 270, again 360 or 0 degree. So the phi diagram we referred. So flux, y axis is flux. When it is at 0 degree, diagram A, what we got? Flux is pi m, maximum value. So while rotating, that is A is rotating in anti-clockwise, B is rotating in clockwise direction, what happened? The flux keep on decreases and becomes 0, right? So both are in opposite, that is 0. That is the diagram where C we referred. Diagram C, it is A at the top, B at the bottom, so the net flux is 0. Still it keep on rotating. A rotating anti-clockwise, B rotating clockwise direction. So it will goes to the negative maximum pi m, maximum value, but in the negative side, minus pi m, what we discussed in the diagram D. Still it keep on rotating here. So the flux is increasing in negative direction and become again 0. That refers the diagram E, right? Again the same process repeats. From 270 to 360, the flux is increasing and again reaches maximum value. This is the original position, right? So at 0 degree, the flux is maximum pi m. While rotating clockwise and anti-clockwise direction, both are opposite side. The net flux is 0. Still it keep on rotating clockwise and anti-clockwise direction. It will goes to negative minus pi m. Again while rotating, again it's both are opposite. Both are placing in opposite direction. The net flux is 0. Okay. So the flux produced this side is cancelled by positive flux. Produced is cancelled by negative flux. The net flux is 0. After half a cycle, flux A and B will have a resultant flux of minus 2 into pi m by 2, that is minus pi m. After a quadrature of a cycle, again the resultant flux is 0 as shown in the diagram E, and so on, right? So this refers the diagram A. This 0, both are diagonally opposite diagram C. This will diagram D, negative, exactly opposite of diagram A. This will refer the diagram E. Again it is in, both are in opposite, become 0, right? Now we'll go to the remaining value. If we plot the values of resultant flux against theta between the limit 0 and theta 0 to theta 360 degree, the curve similar to the diagram. So this diagram will got. If you draw the curve between angle theta and flux, we'll got this resultant flux. Now we'll go for further analysis. So that's why an alternating flux can be looked upon a composite of two revolving flux, each of half value and revolving synchronously in opposite direction. So we are consider two revolving flux, both are in opposite direction. Initially maximum value pi m, then 0 value, then maximum value in negative direction minus pi m, again 0. So that represented by 4 diagrams. So it may be noted that if the slip of the rotor is S with respect to the forward rotating flux, that is one which rotates the same direction as a rotor, right? So if you refer, there are two fluxes A and B. One that is a rotate in the as a direction of rotor, we can represent that S means then the slip with respect to the backward rotating flux is 2 minus S, right? So the one flux, if you consider as a rotation of the rotor is S mean, another flux will be, the slip will be 2 minus S. So we have S and 2 minus S, the corresponding slips of the two revolving fluxes. One is S, another one is 2S. Each of the two component fluxes while revolving around the stator cuts the rotor and induces the EMF. This production is one torque, right? So these two components will produce the EMF and thereby torque. Now we'll see the torque curve. The graph shows the torque. So this is the slip S is available here. This is the torque, y-axis torque, x-axis slip is 0, this one 2.0. So what we refer S 2 minus S. In this clockwise direction, this is clockwise direction, so the flux produced is positive. So at that time it reaches the maximum value and reduces. In anti-clockwise direction, the flux is negative. The same what we produced in the clockwise, same, but it is in negative. So that due to that we have forward flux and this forward and backward torque, forward torque and backward torque. So this is the result. This is the torque produced. Right. So this is the resultant torque. This is the torque produced by forward torque. This is backward torque. Combination of these two, sum of these two is the resultant flux. So in the clockwise direction we got positive value, in the anti-clockwise direction we got negative value. So we can go for further analysis. This is refer S, this side refer 2 minus S. See the now power developed by the rotor Pg equal to 1 minus S by S into I2 square into R2. So general formula. If N is the rotor RPS, then the rotor torque is given by Tg equal to 1 divided by 2 pi n 1 minus S divided by S I2 square into R2. From the power we can write the torque equation, right? This rotating in RPS, we consider RPS, right? So now we have the two torque S and 2S. Based on that we can go for the further analysis. We know that N equal to Ns into 1 minus S. Brought this 1 minus n in the denominator, so that N divided by 1 minus S equal to Ns. Now write it in reciprocal. 1 minus S by N equal to 1 divided by Ns. Right. So 1 minus S divided by N can be replaced by 1 divided by Ns. Now we'll consider this equation. Now we'll rewrite this equation. 1 divided by 2 pi. The N is written here. 1 minus S by N. This 1 minus S and N is written here. This 1 by S is written separately. I2 square R2. Right. Now the equation is rearranged. It is in the form 1 minus S by N. So this 1 minus S by N, this can be replaced by 1 by Ns. Right. So now what we have, 1 divided by 2 pi S. This S is available here. N 1 divided by Ns I2 square R2. Right. Now we'll go for further simplification. 1 divided by 2 pi Ns. This Ns is written here. This S is combined with this. I2 square R2 divided by S. So finally what we have, this can be written as constant, 1 divided by 2 pi ns, constant. I2 square R2 divided by S. Right. So this is the normal torque developed by the rotor. But what we have, forward torque and reverse torque. Forward and backward torques are available. So from this equation we can easily identify the value of forward and backward torque. So this is a normal equation. Now we'll consider forward and backward torque. TF, forward torque equal to K into I2 square R2 divided by S, as it is. In case of backward torque, minus K, because negative. I2 square R2 divided by 2 minus S, we already referred. The rotor rotating in the same direction, the slip is S, opposite direction, the slip is 2 minus S. So this is the same direction, this is opposite direction, S 2 minus S. So otherwise it can be written as TF equal to I2 square R2 divided by S. That's a synchronous watt, another form. Right. Similarly here, minus I2 square R2 divided by 2 minus S, synchronous watts. This is normal formula, this is in synchronous watts. So the total torque is TF plus TP, forward torque plus backward torque. So from the diagram, the graph what we shown, both torques are resultant torque for the slip between 0 and plus 2. At standstill, S equal to 0 and 2 minus S equal to 1. What we discussed in the diagram is available between 0 to plus 2. The torque is, the slip is what we represented 0 up to plus 2. So at the standstill, S equal to 1, that we know that. Similarly, 2 minus S equal to 1. Now we'll see how this resultant flux is 0 in here, how it is concluded. Hence, forward torque TF and backward torque TB are numerically equal, but being oppositely directed produce the no resultant torque. From the graph we are easily identify that both are same magnitude, but it is opposite. One is positive and another one is negative, so the resultant torque is 0. That explains why there is no starting torque in a single phase induction motor. Right, so the aim of this topic is double field revolving theory is while using single phase, why the resultant torque is 0. So why we are easily identified from the graph. So in the diagram we referred 5 diagrams. Initially pi m, then 0, then minus pi m, again 0. This keep on changing. So the resultant torque is 0, resultant flux. Similarly in the diagram 2 we refer the torque. There also resultant torque is positive, negative, clockwise positive, anti-clockwise negative. So the resultant is 0. From that we conclude no starting torque produced in the single phase induction motor. However, if the rotor is started somewhere, say in the clockwise direction, the clockwise torque starts increasing and the same time the anti-clockwise torque starts decreasing. So if we start the motor by using any other way, what happens? The clockwise direction the torque increases, anti-clockwise direction the torque will decreases. Hence, there is a certain amount of net torque in the clockwise direction accelerate the motor to full load. So still, if we start rotate by any other way, any other manner, that's why we are using starting winding. So that the motor is started by the starting winding, thereafter the clockwise direction, definitely there will be some torque is produced. The torque will accelerate the motor to the full speed. So that motor will retain, the motor will accelerate. That will guide the motor to rotate in the full speed. So if it is single phase used in the single phase induction motor, the net torque produced, net flux produced is 0. If it is started by any other manner, either capacitor start or induction start or any using the starting winding, once the motor start rotates, what we concluded, in clockwise direction the torque increases gradually, anti-clockwise direction torque decreases gradually. So after starts rotating, definitely the torque available in the clockwise direction accelerate the motor to attain the full load speed. So that is the important conclusion from this topic, double field revolving theory. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see how to make the single phase induction motor self-starting. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Making single phase induction motor self-starting. Single phase induction motor is a not self-starting. It will not start. Selfly it will not start like other three-phase motor. To overcome this drawback and make the self-starting, it is temporarily converted into two-phase motor during the starting period. So we are making into two-phase winding. We will see why we are making two-phase winding. So let us consider we are applying the AC voltage. We know that the AC voltage alternating in nature, positive off cycle, negative off cycle. Let us consider it's a current. So during positive off cycle of the current, the positive flux will be produced, plus pi. During negative off cycle, what will happen? The flux will be produced, but it's negative flux, minus pi. So the sum of these two will be 0. Net flux will be 0. During positive off cycle, positive flux is produced. During negative off cycle, negative flux is produced. So the total average is 0. So due to that, this motor is not self-starting if it is single phase winding. So if it is only one phase winding, if you apply the single phase AC, what will happen? The net flux is 0. So we are making into two phase winding. There are two windings are there. In between two winding, there is a phase difference of 90 degree will be there. First phase it is the current is applied at 0 degree. Second phase it is applied at 90 degree by connecting the capacitor. The capacitor will lead the current. There is a phase difference of 90 degree will be done by the capacitor. So one phase applied with 0 degree, another phase applied with 90 degree. There is a phase difference of 90 degree. So due to these two, what happened? See this here, the flux is increasing, means another phase flux is decreasing. At this portion the flux is decreasing, but another flux is start increasing. So there will be a net flux will be always there. If it is only one phase, that net flux is 0, but here two phases available and there is a phase difference of 90 degree also. So always there is a net flux will be available. That flux will be used to start the motor. That is the concept of converting the single phase motor into two phase motor. So one phase applied 0 degree, another phase applied 90 degree. So always there is a net flux will be there, that is used to start the motor, right? So only one phase means the net is 0. Two phases with 90 degree means always there will be flux will be there. See here it is decreasing in negative direction, but another flux is positive. So always there is a net flux will be there. Now we'll see the diagram how to convert into two phase winding. Then what is the procedure? So this is the rotor, rotating part, as a stator, stationary part. So there is a air gap. So in the stator we have two set of winding. Main winding, this refers main winding. This is the starting winding. This shaded portion is nothing but starting winding. On both the side we have starting winding. These two are main winding. So this is connected through the capacitor. So there is a phase difference of 90 degree will be made between starting winding and running winding. That will make the motor self-starting. The flux will be produced. And also this starting winding is connected with one centrifugal switch. Once the motor start rotating, due to the force, the centrifugal switch will disconnect this starting winding. Thereafter only main winding will be available. So the ceiling fan also a induction motor having two windings, starting and running winding. We know that we are connected with capacitor. Sometimes the ceiling fan is rotating slowly, means the capacitor may fail. So we can replace the capacitor. So the capacitor in the ceiling fan make the current leading in one winding. so that there is a phase difference. It will make a net flux available in between the main winding and starting winding, so that the fan start rotating. Thereafter, due to centrifugal force, the starting winding is disconnected. Right. Now we'll see the some description. The stator of a single phase motor is provided with extra winding known as starting or auxiliary winding, in addition to the main or running winding. So we have two windings: starting winding, running winding, or otherwise auxiliary winding, main winding. The two windings are spaced 90 degree electrically apart and connected in parallel. That will be done by the capacitor. By connecting capacitor, we are able to make 90 degree electrically the phase difference between starting and running winding. So it is so arranged that phase difference between the current in two stator winding is very large, that is 90 degree. So there is a phase difference of 90 degree. Hence the motor behave like a two-phase motor. So two-phase motor with 90 degree phase difference means always there should be the flux will be available. If it is only one winding with one current means the net flux is zero due to alternating nature. Now it behave like a two-phase motor. These two currents produce revolving flux and hence make the motor self-starting. So that is our main aim, is to produce the revolving flux. Because of two windings with two different current with phase difference of 90 degree, the revolving flux is produced and make the motor self-starting. Right. How to convert, how to make a 90 degree phase difference? There are many methods by which the necessary phase difference between the two current can be created. How to create the phase difference? There are two methods available. So many methods available. Mainly we have two methods. Split phase machine. The phase is splitted. Another one, capacitor start induction run motor. So the capacitor will make the phase difference of 90 degree. In another case, split phase machine. The separate video available how to make a self-starting using split phase machine. Similarly, how to make a self-starting of induction motor using capacitor start induction run. Separate videos available. Link is given in the description box. In this video, we discuss how to make the self-starting by making single phase winding into two phase with the phase difference of 90 degree, so that always there is a revolving rotating flux that will make the motor to self-start. That can be implemented with two methods: split phase machine, capacitor start induction motor. For these two, separate video available. Subscribe this channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. All the best for your examination. Welcome viewers. In this video, we'll see the equivalent circuit of single phase induction motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic: single phase induction motor equivalent circuit. The double field revolving theory is used to form the equivalent circuit. The double field revolving theory based on the equivalent circuit is drawn. This double field revolving theory is a separate video available. The link is given in the description box. What is that double field revolving theory? When two fields are known, the torque produced by each can be obtained. Double field, that refers, we are referring two fields are available. The difference between these two torque is the net torque acting on the rotor. So based on the two torque, the net torque is the difference between these two torques are available. Then imagine that single phase induction motor is made up of one stator winding and two imaginary rotor winding. So to form the equivalent circuit, we assume that one stator winding is available and two rotor windings are available. Imaginary rotor windings are available. One rotor is rotating in forward direction with a slip of S, while the other is rotating in backward direction with a slip of 2 - S. right? One is forward direction, slip S. Another one backward direction, the slip is 2 minus S. Now there are two types available, with core loss and without core loss. To draw the equivalent circuit, let us assume initially the core loss is absent. Then we'll go with the loss. Now we'll consider without loss. Now we'll see the parameters. Let stator impedance Z1 equal to R1 plus JX1. This 1 refers stator, 2 refers rotor. So the R1 is nothing but stator resistance, X1 is nothing but stator reactance. So the X2 rotor reactance referring stator, R2 rotor resistance referring to stator, right? The number 1 refers stator. Z1 stator impedance is R1 plus JX1. R1 is stator resistance, X1 is stator reactance. Then X2 R2 refers rotor reactance. X2 is rotor reactance refer to stator. R2 is rotor resistance refer to the stator. Now we'll see the further detail. So the impedance of each rotor equal to R2 plus JX2. Earlier we refer R1 X1. Now it is small R2 small X2. So the small X2 is nothing but X2 divided by 2. Similarly, R2 is R2 divided by 2. That is, what is X2? This is a stator reactance refer to the stator. Rotor reactance refers to the stator. Right? Now it is each impedance of each rotor is small x2 plus small r2 plus jx2. So that is given in terms of capital X2 by 2, capital R2 by 2. So this resistance of forward field rotor is R2 by S. Backward field is R2 by 2 minus S. We already discussed S is for forward direction, reverse direction 2 minus X. Now the core loss is neglected. So therefore R0 is neglected. We have only X0. R0 is not available. X0 is nothing but no load. X0 by 2, that is actual magnetizing reactance. This refers to magnetizing reactance. So we have stator impedance Z1, that is R1 plus JX1. Then we have X0, actual magnetizing reactance. Then we have this R2 and X2. This R2 and X2. Based on that, we can draw the equivalent circuit. Now we will refer the equivalent circuit. So this is applied voltage V, current I1 flowing through the stator. R1 X1, resistance of the stator, X1 is reactance of the stator. Now already we discussed that there are two fields available, forward and reverse, forward and backward. So based on that, this is refers the forward. This is backward. Forward voltage, backward voltage. We are already referred to imaginary rotors. So this is a X0. This R0 is neglected because of core loss, because of neglecting core loss. So only X0 is available. This is actual magnetizing reactance. Then this is referred to the forward direction, so that R2 by S X2. Impedance and resistance of the rotor in forward direction. Current is I2F, refers forward current. ZF refers forward, impedance of the forward rotor. Similar to, we have ZB, impedance of reverse, backward rotor. I2B refers current flowing through the rotor in backward direction rotor. X0 is common. So because of backward, we refer R2 by 2 minus X and X2. This S refers forward direction, 2 minus S refers reverse direction. So this entire the equivalent circuit, what we have, this current applied voltage, current through the stator, impedance, resistance and reactance of the stator. Then rotor side, two things, forward and backward. VF, ZF, VB, ZB, I2F, I2B. S refers forward direction, 2 minus S refers reverse direction. So based on that, we can find the parameters one by one, that is ZF and ZB, impedance of forward rotor and impedance of backward rotor, thereby other parameters. So first we'll see the impedance of forward rotor. What is the impedance of forward rotor? Refer the diagram. This R2 by S and X2 connected in series, that is in parallel with X0. These two are in parallel. X0 is parallel with R2 by S plus X2. So based on that we can find ZF. So that is given. R2 by S plus JX2 connected in series, that is in parallel with X0. So this is R1, this is R2. R1 into R2 divided by R1 plus R2. Otherwise Z1 into Z2 divided by Z1 plus Z2. So R2 by S plus JX2 plus JX0. So this refers the impedance of forward rotor ZF. Similarly we can find impedance of reverse rotor. So this is the impedance of forward rotor is given. Now impedance of backward rotor ZB. R2 divided by 2 minus X plus JX2. These two are connected in series, that is in parallel with X0, JX0. So Z1 into Z2 divided by Z1 plus Z2. Now we can segregate the real term and imaginary term. J terms are combined together. So R2 by 2 minus S plus J X0 plus X2. These two are combined. Here also it is combined. Now we calculated ZF and ZB, impedance of forward rotor and backward rotor. Now we'll see the further parameters. So at start or standstill, that is at the beginning, S equal to 1 and 2 minus S equal to 1. There is no speed, right? This fully slipped. So speed is 0, so that S equal to 1. That means it's not rotated at the standstill or start. So ZF equal to ZB. Based on that, both are equal. VF equal to VB. Forward impedance, backward impedance, both are same. Forward voltage and reverse voltage, backward voltage are same. In running condition, VF is almost equal to 90 to 95% of applied voltage. So when it is running condition. So under that, what is the equivalent? Z equivalent Z1 refers stator, ZF plus ZB. These two refer rotor, forward rotor impedance, backward rotor impedance. So this is the total equivalent impedance of a entire circuit. Now we'll see the current flowing through forward as well as backward. I2F, current through forward rotor refer to the stator. What is I2? I equal to V by R, VF. I2F refers forward direction. In that the voltage is VF. The resistor is, the impedance is R2 by S plus JX2. This S refers forward. In case of backward, 2 minus S. So VF equal to I1 into ZF. How to find this VF? V equal to I into R. The current flowing through the equivalent circuit from the supply into ZF. ZF is nothing but forward, impedance of forward rotor. So we can able to find current as well as forward voltage, thereby current. Similarly backward, current through backward rotor, VB divided by R2, 2 minus S. We already discussed S refers forward rotation, 2 minus backward rotation. Similarly the backward voltage I1 into ZB, right? So initially we consider stator, thereby rotor, two rotors, forward and backward. Then we calculated forward impedance, backward impedance, ZF and ZB. From that we calculate the Z equivalent, total impedance of the circuit, Z1 plus ZF, ZB. These two refers rotor, this one refers stator. Then we can able to find forward voltage. From that we can find forward current, reverse voltage, thereby reverse current. Now we'll see the power calculation. Now we calculated voltage, impedance, current. All the parameters are calculated. From that we are able to calculate power, thereby torque. Now consider PF is the power input to forward field rotor. Similarly PB is the power input to backward field rotor. This PF can be given as, we know that power equal to I square R. Here forward, so that I2F square into R2 divided by S, because of forward field divided by S. Similarly PB equal to I2B square, backward current, R2 divided by 2 minus S. For backward we are referring 2 minus S. Here S 2 minus S. So forward field rotor power and backward field rotor power is given. So the PM, mechanical power developed, equal to 1 minus S into net power input. That is PM equal to 1 minus S into PF minus PB. The difference between forward field rotor power and reverse field is the net power input. Then P out is nothing but PM, mechanical power input, minus mechanical loss minus core loss. From that we can able to find P out. So first we calculated PF and PB. The difference between these two is the net power input, multiplied by 1 minus S gives the mechanical power input. From mechanical power input, if you subtract mechanical loss and core loss, we will get power output. Now we'll see the torque. Forward torque TF equal to, is a general formula, PF divided by 2 pi n divided by 60 Newton meter. Similarly TB equal to PB minus divided by 2 pi n divided by 60 Newton meter. So the net torque is difference between these two, TF minus TB. Similarly we can find the shaft torque, TSH, P out divided by 2 pi n divided by 60. From power output and speed we are able to find the shaft torque, P out. P out we already calculated. P out divided by 2 pi n divided by 60 Newton meter will give the shaft torque. Then efficiency, it's a general formula. Net output divided by net input into 100. Percentage of efficiency means multiplied by 100. So finally we calculated efficiency also. So this is coming under without core loss. Now we'll see with core loss what is the equivalent circuit. For with core loss, if core loss is to be considered, then it is necessary to connect a resistance R0 in parallel with X0. In previous case we neglected the resistance, we consider only X0. Now we need to consider resistance, that is parallel with X0. This R0 is nothing but small r0 is R0 divided by 2. So based on that we can see the equivalent circuit. So this is nothing but R1 X1, that is referring the stator. These two refer the rotor. I1 is the total current flowing, V is the applied voltage. Now I know that rotor we have two parts, forward and backward. So this is a forward, ZF, forward rotor impedance, reverse rotor, backward rotor impedance, ZB. Similarly I2F means forward, I2B means backward, VF, forward voltage, backward voltage. In previous case we have only X0, now R0 is connected in parallel. So what is the total impedance Z0? That is nothing but ZOF, which is refer. These two are connected in parallel, so that refers Z0F. That is in parallel with this network R2 divided by S into plus X2. Right? In the earlier case we don't have R0. So these two are in parallel, that is in parallel with the other network, that is the ZF. Similarly ZB. Now we'll see that equivalent impedance. So this ZOF, equivalent impedance of existing branch in forward rotor, ZOF equal to R0 parallel with JX0. So this time not available in previous case. We don't have R0. Now R0 is there. So these two are in parallel. That is given by ZOF. This ZOF is parallel with R2 divided by S plus JX2. Right? So these two are parallel. These two are parallel is given by Z0F. That is parallel with this network in case of forward rotor. In case of backward rotor, Z0B R0 plus JX0, both are same. So this network is parallel with the another network R2 divided by 2S plus JX2, that is ZB. Right? Forward rotor impedance ZF equal to Z0F, that is nothing but parallel of R0 and X0, that is parallel with this network. Similarly ZB. So we are able to find the ZF and ZB, forward rotor and backward rotor impedance. So in this video we discuss equivalent circuit of a single phase induction motor based on the double field revolving theory. Stator with two imaginary rotors referring with S, slip S, 2 minus S. Then with core loss, without core loss, we discussed the equivalent circuit. We calculated the impedance followed by power, torque, shaft torque, then efficiency. Similarly with core also. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. All the best for your examination. Welcome viewers. In this video we'll see the test performed on the single phase induction motor in order to draw the equivalent circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we go to the topic. To draw the equivalent circuit, we are going to perform the test on the induction motor, single phase induction motor. The following tests are conducted on single phase induction motor to draw the equivalent circuit. There are two tests we are going to perform: no load test or open circuit test, blocked rotor test or short circuit test. So the name itself is able to understand. It's a no load. Load is not applied. Second one, blocked rotor. Rotor is blocked. So first we will see the no load test. So the motor is run on no load. Load is not applied. Rated voltage is applied and readings of voltmeter, ammeter and wattmeters are noted. The circuit diagram is not given here, but the thing is we have to apply no load and wattmeter, ammeter, voltmeter is connected. We need to measure the value. The thing is rated voltage is applied. In case of blocked rotor test, rated current will be applied. Now we are applying rated voltage. So we are measuring voltage, voltmeter, ammeter and wattmeter reading. This refers no load voltage, no load current and no load power. V0, I0, W0. So W0 equal to V0, I0 cos pi naught. No load power equal to no load voltage, no load current into power factor at the no load. So from this we can find cos pi naught. That is, you brought this V0, I0 in the denominator. So omega naught divided by V0, I0 equal to cos pi naught. So cos pi naught equal to omega naught divided by V0, I0. That is nothing but no load power factor. So we are able to find the no load power factor from these three readings. No load speed is almost equal to the synchronous speed. No load speed means the motor is rotating at the synchronous speed. So therefore for practical purpose, slip S can be assumed as 0. There is no slip. 1500 rpm means the motor will rotate at 1500 rpm itself at the no load condition. So the slip is 0. There is no slip. We know that there are two rotor circuit available: forward rotor circuit and backward rotor circuit. We are assuming the double field revolving theory in single phase induction motor. Based on double field revolving theory, forward circuit, rotor circuit and backward rotor circuit both are rotating in opposite direction. Separate video available for the double field revolving theory. So based on that, for the forward rotor circuit we are assuming R2 by S. S equal to 0, so it become infinite. For backward rotor test, R2 divided by 2 minuses. We are taking 2 minuses. Here S equal to 0. So R2 divided by 2 is not S. R2 divided by 2. So forward circuit, the resistance is infinite. Backward circuit, the resistance is R2 divided by 2. Now we'll go for the further detail. In forward circuit, R2 by S plus JX2 get eliminated because it is infinite, it got eliminated. In backward circuit, X0 is higher than R2 divided by 2 plus JX2. Therefore, current tends to flow through the low impedance path. So X0 of the branch is eliminated. Right? So in the forward path, this R2 by S plus JX2 is eliminated. In the backward path, X0 is eliminated based on the condition what we discussed, R2 by 2 and infinite. Now we'll see the equivalent circuit based on this assumption. So this is applied voltage, no load voltage, no load current, R1 X1, that refers the stator resistance and stator reactance. So this one refers the forward rotor circuit, this one refers the backward rotor circuit. We then know that this X0 we are having, this R2 by S X2 is eliminated in this for a forward rotor circuit. For a backward rotor circuit, X0 is eliminated. The current is flowing through R2 by 2 X2. Right? So based on these two assumptions, we can further simplify the circuit. Circuit is redrawn. So I0 voltage V0, no load voltage and no load current, this stator R1 X1. This X0 based on the forward rotor circuit. R2 by 2 X2 is based on the backward rotor circuit. So what is available? It is redrawn. V0, I0, R1 X1 is X0, that is AB, under the point AB. Then R2 by 2 and X2. So all are connected in series. R1 X1, X0, R2 by 2 X2. Right? In that X0 is connected across AB. This network is connected across CD. So that is given. Stator, forward rotor circuit, backward rotor circuit. So V0 can be written as VAB. We will take this VAB, voltage across the forward rotor circuit. Then remaining R1 plus R2 by 2, R1 plus R2 resistive value plus J reactance value, X1 plus X2. So we can write that VAB, we will write VAB. So this term is brought that side, so negative. So VAB equal to V0 minus I0 of R1 plus R2 by 2 plus J X1 plus X2. Now we'll find the VAB value. Our aim is to find the VAB value. So VAB equal to I0 X0. Voltage across that is voltage across is that no load voltage and X0 is flowing. V equal to I into R. So X0 equal to VAB by I0. We know that X0, small x0 equal to capital X0 divided by 2, because we have two rotor circuit, forward and backward. So it is exactly divided into 2, X0 by 2. From that X0, capital X0 equal to 2 times of small x0. This X0 is nothing but VAB by I0. So 2 into, substitute this, X0 equal to VAB by I0. So from that we are able to find X0 equal to 2 of VAB divided by I0. So we are able to find the X0 value by using the no load test. And then we'll go for the blocked rotor test. The another two parameter we can able to find from the blocked rotor test. So in that, rotor is held tight so that it does not rotate. Say that is a rotor is blocked. In previous test, the load is not applied. Now the load is applied. Rotor is held tight. It is fully blocked. Voltage is adjusted to apply the rated current. In previous case, we apply rated voltage. Because of short circuit, we apply rated current. The readings of voltmeter, ammeter and wattmeters are noted. Right, like previous case. In this case, here VSC, short circuit voltage, short circuit current and short circuit power. In previous case, no load voltage, no load current and no load power. But now it is blocked so that it represents the short circuit. Now based on that, we'll see that the rotor is blocked, so n equal to 0, s equal to 1. Completely there is no speed, fully slipped, s equal to 1. In previous case, the motor is rotating at the rated speed, so no slip, 0. All speed is equal to the rated speed, so there is no slip, no, speed is not slipped. But here the entire speed is slipped, that is speed is 0. So now we need to substitute the s value equal to 1. Previous case s equal to 0. So for forward rotor circuit we know that R2 by S. Now s equal to 1. So it is R2. For backward rotor circuit R2 divided by 2 minus S. Now s equal to 1. So 2 minus 1, 1 R2. So for backward and forward both the circuit, the resistor value is R2. Here also R2. Now X0 is higher than the rotor impedance. So that is neglected. X0 is the higher than the rotor impedance. So that X0 value is not included here. So based on that we can draw the equivalent circuit. ISC, VSC. Short circuit voltage, short circuit current. R1, X1 refers the stator resistance and stator impedance. Reactance, stator reactance. Then this X0 is neglected. X0 is higher than the rotor impedance, so it is neglected. Only we have this R2, X2. We already calculated for both the case R2, the value is R2. So R2, X2. So R2 plus R2, we here add the resistor value. R2 by plus R2 is 2R2. That is equal to capital R2. Know that small r2 equal to capital R2 divided by 2. So capital R2 equal to 2 times of small r2. So 2 into small r2 can be written as capital R2. Similarly, 2x2, small x2 can be written as capital X2. So now we calculated R2 value and X2 value. This X0 is neglected. These R2 are added together, the X2 are added together. Now we will go for the further readings. So the short circuit power WSC equal to VSC ISC into cos pi SC. So from that cos pi SC can be written as WSC divided by VSC into ISC. Blocked rotor power factor. Earlier case no load power factor, now it is blocked rotor power factor. Z equivalent equal to VSC by RSC impedance. From the and R equivalent equal to WSC divided by I square. That is power equal to I square R. Power equal to I square into R. So that R equal to power divided by I square. So we are able to find the resistance, equivalent impedance. And we know that the R equivalent equal to R1 plus R2. So that R2 equal to R equivalent minus R1. From the rotor resistance refer to the stator. So we are able to find the R2 value. Then X equivalent equal to square root of Z equivalent minus R equivalent. This is a normal impedance formula. Right? Reactance equal to square root of impedance minus resistance. So assume that X1 equal to X2. So that X2 equal to X equivalent divided by 2 because both are equal. So now we calculated R equivalent, R2 value as well as X2 value. That is our aim. We need to find the R2 and X2 value. In the previous test, no load test, we calculated X0. Here we are calculating R2 and X2. R1 AC equal to 1.5 times of R1 DC. That is referring AC and DC circuit. In case of AC and DC, this is the relation. So in this video, we discussed the test performed on the single phase induction motor, no load and blocked rotor test. From no load means the load is not applied, motor rotating at rated speed, slip equal to 0. Based on that, we can measure no load current, no load voltage, no load power. From that we can find no load power factor. Finally, we calculated X0 value. In blocked rotor test, the rotor is completely blocked, speed is 0, so slip equal to 1. That is substituted. We are able to measure short circuit current, short circuit voltage and short circuit power. Then finally we calculated R2 value and X2 value. So by using this parameter we are able to draw the equivalent circuit of a single phase induction motor. The explanation of equivalent circuits, separate video available. The link is given in the description box. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. All the best for your examination. Welcome viewers. In this video we'll see the solved problem based on the test on single phase induction motor. That is in order to draw the equivalent circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Solved problem. Test on the single phase induction motor in order to draw the equivalent circuit. Now see the statement of the problem. A 220 voltage single phase induction motor has the following test result. We know that we have two tests available, no load test, blocked rotor test. No load test, that means no load voltage, no load current and no load power. V0 220 voltage, I0 6 ampere, W0 350 watts. Then blocked rotor test, it is nothing but a short circuit. Short circuit voltage, short circuit current and short circuit power. VSC 125 voltage, ISC 15 amps, WSC 580 watts. Then stator resistance is 1.2 with direct current. Estimate the power factor and efficiency when the slip is 0.05. So we need to find power factor, then efficiency. The slip is given as 0.05. I will see the given data based on the statement. The data given is V rated V1 220 voltage, V0 220 voltage, because in no load test we are applying rated voltage, so that V1 equal to 220, I0 equal to 6 ampere, W0 is 350 watts, VSC 125 voltage, ISC 15 ampere, so this is the rated current, WSC 580 watts, R1 DC equal to 1.2 ohm, R1 AC equal to 1.5 times of R1 DC, the formula is available. So that is equal to 1.5 into 1.2, it is 1.8 ohm. R1 DC is 1.2 ohm, R1 AC is 1.8 ohm. Using the formula we calculate. S equal to 0.05. Right. First we will find the power factor. Power factor is cos pi 1. This, how will you find this cos pi 1? I1 equal to V1 by Z equivalent. By calculating V1 and I1 we are able to find cos pi 1. I1 is V1 by Z equivalent. V1 is nothing but 220 voltage. It is 0 degree already given. Then what about the Z equivalent? Z equivalent is Z1 plus ZF plus ZB. Z1 is nothing but stator impedance. ZF is impedance of the forward rotor circuit. ZB is the backward rotor circuit. We know that the single phase induction motor is working on the double field revolving theory. That is one stator with two imaginary rotors. One is rotating in forward direction, one is rotating in backward direction. That's why we have Z of ZB. Right? So in order to calculate Z equivalent, we need to find Z1, ZF, ZB. First we will see how to find the Z1 value. Z1 is nothing but R1 plus JX1, stator resistance and stator reactance. R1 is given 1.5, 1.8 ohm. The X is X1, X2 is not given. That is equal to X equivalent by 2. What is that? X1 equal to X2. Under no load condition, there is no slip, so X1 equal to X2. So X equivalent equal to X1 plus X2. Both are equal. So that 2x1. So X equivalent equal to 2x1. So x1 equal to X equivalent by 2. So now we need to find X equivalent. So that we are able to find the x1. From that we can find Z1. Right? So first we are finding Z1. Then we will go for ZF. Then by ZB. Right? Now we will see how to find the X equivalent. So X equivalent equal to square root of Z equivalent minus R equivalent square. We know that this is the reactance equal to square root of impedance square minus resistance square. Actually, what is the formula? Z equivalent square equal to X equivalent square plus R equivalent square. So from that we calculated this reactance. Z equivalent equal to VAC by ISC, short circuit voltage by current. 125 by 15, it is 8.33 ohm. Then R equivalent equal to WSC by ISC square, that is power equal to I square R. From that R equal to power by ISC square. Using that formula we are finding. WSC is 580. Short circuit current is 15 square. That is 2.577 ohm. Now we calculated Z equivalent and R equivalent. From that we can easily find the X equivalent reactance. So these values are substituted. Then we calculated X equivalent equal to 7.9245 ohm. So from that we can able to find X1 and X2, thereby Z1. X1 equal to X2 equal to X equivalent divided by 2. This value divided by 2, that is 3.9622 ohm. So now we are able to, we have the value of X1, X2 as well as R1. So we can easily find the Z1. Z1 equal to R1 plus JX1, that is equal to 1.8, what we already given, this value is already given. Then X1, what we calculated, 3.966 ohm. Right? Now we calculated the Z1 value, stator. Then we'll go for forward rotor circuit, ZF. Then we'll go ZB. Right? So ZF equal to, the formula is JX0 into R2 by S plus JX2 divided by R2 by S plus JX2 plus X0. So this formula, this equivalent circuit of induction motor, separate video available. In that the explanation given how we got this formula. That is nothing but these two are in parallel. Z1 into Z2 divided by Z1 plus Z2. Based on that it is calculated. So in that X0 we need to find. We need to find the X0 value. How to find the X0 value? VAB equal to I0 into X0, so that X0 equal to VAB by I0. This formula also available in that video. Right. So in order to find X0, we need to find VAB as well as I0. What is VAB? V0 minus I0 of R1 plus R2 by 2 plus JX1 plus X2. So this divided by S refers to forward rotor circuit. 2 minus S means backward rotor circuit. Right. So in this formula V0 is available. It's given 220 voltage. That is no load voltage is nothing but rated voltage. Right. Then how will you find the I0? I0 equal to I0 of angle pi naught. Negative because I0 is lagging the voltage. The I0 value is given 6 ampere, no load voltage, no load current. Pi naught equal to cos inverse omega naught divided by V naught I naught. This is a general formula. Actually what is that? This omega naught equal to V naught I naught into cos pi naught. From that we calculated. So substituted, values are substituted. We calculated 74.62 degree. So that I0 equal to 6 of angle 74.62. Right. Now we calculated the I0 value. We now need to find VAB. By calculating VAB, we are able to find I0. By finding I0, we are able to find the ZF. Right. Now we'll see how to find the VAB value. In order to find the VAB, what we need is R1, R2 value, X1, X2 value. R1 value is given 1.8 ohm, but R2 is R2 divided by 2. That is equal to R2 we need to find. In order to find the small r2, capital R2 is needed. What is that? R equivalent equal to R1 plus R2. So this is the total resistance of the circuit considering stator and rotor. From that R2 equal to R equivalent minus R1. R equivalent already we calculated 2.577 minus that R1 is 1.8. So it is 0.777 ohm. So that R2 equal to capital R2 divided by 2. So it is 0.3885. So now calculated R2 value. R1 is already given, R2 is calculated. Similarly, we need to find X1 and X2. X1 is already given. X1 value is already given. X1 equal to X1, small x1 equal to capital X1 equal to capital X2 equal to X equivalent by 2. Right? That is 3.9662. It's already calculated. In previous case, it is already calculated. Now see this, all the values are available. R1, R2, X1, X2. Right? Now substitute all this value. V0 is no load voltage, 220 rated voltage. Current just now we calculated. R1 is 1.8. R0, R2 is 3.333885 we calculated, plus J is X1 3.9662, X2 1.9811. Right? This one we calculated, X1 we calculated, X2 already available. So now all the values are substituted. By simplify, we can simplify this. These two can be simplified, these two can be simplified. So by simplifying that, we got this value 220 voltage, and these two values are simplified, and this is converted into rectangular form. In order to multiply 6 with angle of 74.62 is converted into rectangular form. Now we can multiply this. Real term and image are multiplied. When it is multiplied, we got this value. This polar form also converted into rectangular form. 0 degree simply J0. So by adding this, we got this value, that is converted into polar form. Polar form, rectangular form converted into polar form, it is 182.4 with an angle of 0.653. Now we calculated VAB also, right? So from that we can easily calculate the ZF. Our final aim is ZF. X0 equal to VAB by I0. VAB just now we calculated. I0 also calculated. That is 30.4 with an angle of 75.273. X0 equal to 2 into X0. Capital X0 equal to 2 into small x0. So 2 into 30.4, it is 60.8 ohm. Right. Now all the values are available. So now we can able to find the ZF, forward rotor circuit impedance. So what is the result of Jx0 into R2 by 2 plus Jx2 divided by R2 by S plus J of X2 plus X0. That is nothing but Z1 into Z2 divided by Z1 plus Z2. Now all the values are available. X0 is 30.4. R2 we calculated 0.3885 plus J 1.9811. Then R2 by S. This R2 by this is not 2, this is S value 0.05, right? So here also it is substituted. Now we can simplify this. So these values are multiplied, then it is simplified like this. Now we can divide these two by converting to polar form, then you can divide. So we got this value, that is multiplied inside, so that 6.4752. I think this simplification you know very well. So these two are divided, so this one should be converted into polar form, this also converted into polar form. Magnitudes are divided and angles are subtracted, again that is converted into polar form, right? So this multiplied inside. So finally we got 6.4752 plus J 3.41088. So this is the forward rotor circuit impedance. Similarly we can find the ZB. That will be easier because here more values are we already calculated. X0, X1, X2 are calculated. So we can easily calculate the ZB value. ZB equal to Jx0 R2 divided by 2 minus S. That is the only difference. Backward rotor circuit. Forward rotor circuit R2 by S only. So these all the values are we know. Only the difference is 2 minus 6. So that is substituted. All the values are substituted. Then it is simplified. So again same thing, it is directly given. This term should be converted into polar form. This term should be converted into polar form. Then divide, subtract the angle. So we will get the resultant. That is again converted into rectangular form. Right. Now it is multiplied inside. So that what we got, 0.17556 plus J 1.86048. Right, now we calculated ZB also. So Z1, ZF, ZB, three parameters are calculated. Now we can go for Z equivalent. Now we'll see how to, from these three parameter, we'll find the Z equivalent. So we can now able to find the Z equivalent. Z1, ZF, ZB is already calculated. From that we can find the Z equivalent. Z equivalent equal to, substitute the value Z1, ZF and ZB. Now add the real term and imaginary term, so that this 8.45076 plus J 9.2234. This rectangular form is converted into polar form, so that we got magnitude is 12.5 and the angle is 47.53. So now we calculated Z equivalent. Our first parameter we need to find the power factor. So see, I will see how to find the power factor. So from Z equivalent we are able to find I1 equal to V1 by Z equivalent. V1 is already given, 220 voltage. Z equivalent what we calculated. So by dividing this 220 divided by 12.5 we got 17.6 with an angle of. So this divided means you have to subtract 0 minus 47.53. So it is minus 47.53. So the magnitude is what we got, 17.6 ampere. I1 is nothing but current flowing from the input, this stator. So power factor equal to cos pi 1 equal to cos of, this is the pi 1 value, right? This angle pi 1 minus 47.53. So it is 0.675 lagging, because of inductance it is lagging. Given us lagging. So one parameter we calculated, efficiency, the power factor. Next one we need to find the efficiency. Now we'll see how to find the efficiency. So we know that efficiency equal to power output divided by power input into 100. What is the power output? Power output equal to mechanical power input minus rotational losses. Then power input is V into V1 I1 cos phi. So these values are already available. We need to find P out, PM minus rotational losses. What are the rotational losses? It's nothing but no load loss, omega naught, 350 watts. So this can be taken from no load test. Under no load, losses happen, that is called a rotational loss. That is the constant loss. There is not vary with the load. So that we can take omega naught as a rotational loss. Then we have to find the net power is nothing but the difference between forward power and forward rotor power minus backward rotor power. By finding PF and PB we are able to find the net power. So PF equal to I2F square into R2 by S. We know that F refers forward rotation, forward rotor circuit. For forward rotor circuit we are divided with S. I2B square divided by R into R2 divided by 2 minus S. This B refers backward rotor circuit. For that backward rotor circuit we are dividing by 2 minus S. Right. Then how will you find this I2F? This power is calculated from this formula. In that what we need is current, forward current and backward current. Forward current is Vf divided by R2S plus Jx2. Similarly, backward current I2B equal to Vb divided by R2 divided by 2 minus S plus Jx2. Right. From that we can able to finding these two we are able to find the current, forward rotor current and backward rotor current. Now we'll see the further detail. In order to find the I2F and I2B, what we need is Vf and Vb, forward voltage, reverse rotor circuit voltage. So first we will find Vf and Vb, then we'll go for I2F and I2B. So Vf equal to I1 into Zf. This I1 value we know, just now we calculated. In order to find the power factor, we calculated I1. Zf also already calculated. Forward rotor impedance and Zb also we already calculated. So from that we can easily calculate Vf. So this is the current value, 17.6 angle 47.53. Zf is 6.475 plus J 3.4108. So this rectangular form is converted into polar form so that we can multiply these two magnitudes, adding these two angles. For multiplication we have to add the angle. So it is 128.8056 with an angle of 19.76. Similarly VB, I1 into ZB. ZB also already calculated. That is 0.1755 plus J 1.86048. This rectangular form is converted into polar form. These two magnitudes are multiplied, angles are added together. That is 32.88 with an angle of 37.079. Now we calculated Vf and Vb. From that we can easily find the I2f and I2b. Now we'll see how to find the I2f. I2f equal to Vf. Just now what we calculated, R2 divided by S plus Jx2. All these values are available. These values are substituted and further simplified. Then this rectangular form is converted into polar form. Here these two magnitudes are divided. Is divided, so it is 16.0645. The angle what we need to subtract 19.76 minus 14.30. For multiplication angles are added, for division the angles are subtracted. So it becomes 34 minus 34.06. Similarly we can find the ZB value. VB divided by R2 divided by 2 minus S. Backward reverse 2 minus S plus Jx2. All the values are substituted and simplified. Now we need to convert this rectangular form into polar form. So that is converted into polar form. Now divide this two parameters. So it is 16.5148 magnitude. Angle we have to subtract 37.079 minus 84.258. So it is, we got negative value, minus 47.179. So now we calculated forward rotor current and reverse backward rotor current. From that we can find the forward rotor power and reverse rotor power. Pf equal to I2f square into R2 by S. Here R2 by 2 minus S, backward circuit. So this value what we calculated is substituted here into R2 value and S value is given 0.05. So it is 2005.1896 watts forward rotor power. Similarly reverse rotor power is 2 minus S is substituted. So what we calculated after simplification we got 54.33 watts. So the net power equal to 1 minus S into Pf minus Pb. So these values are substituted. So final net power is 18,853.31662 watts. Right. So that the P out we can calculate. P out equal to Pm minus rotational losses. After if we subtract the rotational losses we get the total output power. The rotational losses already given is a no load power 350. So 1503.3166 watts. So this is the net power output. What is the net power input? P in V1 I1 cos pi 1. These three values are already available. This pi 1 also we calculated power factor. So 2614.3744 watts. Now we have P in as well as P out. So you can easily calculate the efficiency. Efficiency is P out divided by P in into 100. P out is 1503.3162. P in is this value 2614.374 into 100 is 57.5 percentage. So the second parameter, this efficiency also calculated 57.5 percentage, right? So the two parameters, power factor and efficiency calculated. So in this, we discussed the solved problem based on the single phase induction motor. The test results are given, no load and blocked rotor test. From that, we are able to find power factor and efficiency. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. All the best for your examination.